Dear students, I am Kavita B.S., Assistant Professor, Department of Physics of Government Trusted College, Tiptur. In this class, I will explain the derivation of expression for coefficient of diffusion. This topic is in BSc course Physics subject paper 3rd, Thermal Physics, Radiation and Optics 1. And this topic is in the lesson Thermal Physics of Unit 1. Let us start the class. Here we have to derive the expression for coefficient of diffusion, and in the previous two sessions we have already discussed about the derivation of expression for coefficient of viscosity as well as coefficient of thermal conductivity. In the same way, we can derive the expression for coefficient of diffusion also. Here, diffusion phenomena can be defined as due to the difference in molecular density in different part of the gas will leads to transfer of molecules, gas molecules, or transfer of mass from the region of higher concentration to the region of lower concentration in order to bring about an equilibrium condition or in equal distribution of the gas molecule, and this phenomenon is known as diffusion. Now let us discuss the derivation of equation for coefficient of diffusion. For that, let us consider a gas on a horizontal plane. That means here let us consider a gas on a horizontal plane OX. Here OX represents horizontal plane, and let us assume that this gas is made up of large number of closely spaced layers. Then let us consider a layer at a certain distance from the horizontal plane OX. That layer is B. Let us consider a layer B at a certain distance from the horizontal plane. Let the concentration of the molecules, the concentration of the gas molecules along this layer is N, and it is constant. That is the layer B, which is at a certain distance from the reference plane or horizontal plane, and it has a concentration is N. That is, per unit value, N is the concentration of the gas at the layer B. Then here the term dN by dy is concentration gradient, that is the difference in number of molecules between the gas layers, that is represented by the term concentration gradient, that is dN by dy. In vertical direction, that is in along y axis, the concentration gradient is increases. Then let us consider two more layers P and Q on either side of the layer B. In the next slide, that is, let us consider two layers P and Q on either side of the layer B, and these two layers are at equidistance from the layer B, and that distance is equal to lambda, that is mean free path. We are assuming these two layers are at equidistance and the distance is equal to mean free path. That is due to, in order to avoid the collision of the gas molecules while moving between these two layers. Then N is the concentration at this layer. If N represents concentration, then the concentration of the gas molecules in the layer P is equal to n plus lambda dn by dy. Here n plus lambda dn by dy represents concentration of gas molecules in the layer P. Similarly, the concentration of the gas molecules in the layer Q is equal to n minus lambda dn by dy. These terms represents concentration of gas molecules in the respective layers. Then, since according to kinetic theory of gases, gas molecules are in random motion, then there will be a molecular exchange will take place continuously, and if c is an average velocity of the gas molecule, then number of molecules crossing per unit area of layer B per unit time is equal to 1 by 6 into average velocity into concentration. That is, in an average, number of molecules crossing unit area of layer B in unit time is equal to 1 by 6 into C into concentration. That is, the number of molecules from the layer P crossing unit area of layer B in downward direction is equal to 1 by 6 C into concentration of the molecules in that layer, that is n plus lambda dn by dy. This term represents number of molecules of the layer P crossing unit area of layer B in downward direction in unit time. Similarly, the number of molecules from the layer Q crossing unit area of B in upward direction in unit time is equal to 1 by 6 into C into n minus lambda dn by dy. This term represents number of molecules from the layer Q crossing unit area of layer B in upward direction in unit time. Then, the net amount of concentration crossing unit area of B in unit time is given by J is equal to 1 by 6 C into n plus lambda dn by dy minus 1 by 6 C into n minus lambda dn by dy. Here, this term represents the net amount of concentration crossing unit area of B per unit time, and on simplification we get, that is J is equal to 1 by 6 C into 2 lambda dn by dy. Here plus n and minus 1, n is cancelled with this n, then we have 2 lambda dn by dy term. Hence, finally we get the net amount of concentration crossing unit area of layer B in unit time is equal to 1 by 3 C into lambda dn by dy. Actually, this is nothing but the diffusion. That is, in next slide, by the definition of diffusion, that is, for any gas, the number of molecules crossing unit area of the horizontal plane in unit time is given by, that is J is equal to D into dn by dy. Here, this is nothing but concentration, number of molecules crossing unit area in unit time, and it is directly proportional to concentration gradient. Here D represents coefficient of diffusion, and in the previous slide we have, that is J is equal to 1 by 3 C lambda dn by dy. This is nothing but number of molecules crossing unit area of layer B in unit time. This is nothing but diffusion, or by the definition of diffusion, these two are one and the same, and equating these two we get, and by cancelling the term dn by dy on either side, we get D is equal to 1 by 3 C C lambda, that is diffusion coefficient. Capital D represents diffusion coefficient. Then by substituting the average velocity value, that is root of 8 kT by pi m, and that is lambda, mean free path of gas molecules, kT divided by root 2 pi sigma square p, then on simplification we get D is equal to 2 by 3, 1 divided by sigma square p into root m into kT divided by pi to the power 3 by 2. From this is the expression for coefficient of diffusion. From this equation we can conclude that D, that is coefficient of diffusion, is directly proportional to the 3 by 2 of absolute temperature and inversely proportional to pressure. That is, D is directly proportional to T to the power 3 by 2 and inversely proportional to pressure. Here T is nothing but absolute temperature of the gas. So this is about coefficient of diffusion. Then next, the relation between coefficient of viscosity and coefficient of diffusion. From the relations we have, that is for n eta and d. Here eta represents coefficient of viscosity and d represents coefficient of diffusion. So from the equations, that is eta is equal to 1 by 3 rho c lambda. This is the expression for coefficient of viscosity, and d is equal to 1 by 3 c lambda represents expression for coefficient of diffusion. Then in place of 1 by 3 c lambda in this equation we can substitute capital D, that is coefficient of diffusion. Then eta is equal to D into rho, or D, that is coefficient of diffusion, is equal to eta divided by rho, that is density of the gas molecule. So this equation represents the relationship between eta and D, that is coefficient of viscosity and coefficient of diffusion. So these are the textbooks for your reference. Thank you.